Thank you for coming to check out my presentation. I'm going to be talking today about the influence of mesoscale eddies on energy balance closure. The results I'll be showing today are from the CHEESEHEAD project. That was a project that took place in northern Wisconsin in the summer of 2019. And the objectives were to determine how spatial heterogeneity in the landscape is impacting the Earth's energy balance, and specifically to evaluate the hypothesis that mesoscale eddies are an important cause of energy balance non-closure. And the domain in northern Wisconsin was a 10 by 10 kilometer stretch of heterogeneous forest. And it was centered on one tall tower that has been operating for 25 years, taking flux measurements over the landscape at three levels. And for the summer of 2019, 19 additional Eddy covariance towers were installed above the canopy. And then there was a whole suite of Lidar, SODAR, and radar for measuring atmospheric profiles of different constituents, as well as a really large data set of airborne Eddy covariance. And so the problem I'll be looking at today is energy balance non-closure. And that's simply that in traditional Eddy covariance, it's typical to measure greater incoming energy than outgoing energy, even though we expect them to balance. And so at the bottom, there's the energy balance equation. So net radiation minus ground flux should equal latent heat plus sensible heat plus whatever energy is stored in the system. So one hypothesis for what's causing non-closure is that landscape variance is creating quasi-stationary mesoscale eddies, and that those eddies are not being captured well by a traditional single tower Eddy covariance method. So CHEESEHEAD set out to figure out what's happening by installing lots of instrumentation, including many more towers and, as I said, all sorts of other remote sensing and ground-based measurements. But today, all I'm going to focus on is the tower network, so the energy flux is coming from that, the Doppler wind lidars, and the airborne Eddy covariance. And so the tower network was composed of 19 Eddy covariance towers. They were installed above the canopy. Most of them were installed at 33 meters height above the ground, and they measured sensible and latent heat fluxes, all the components of net radiation, and ground flux, and they were installed over a variety of different surface types. So to get a picture of what this area looks like, this is an aerial photograph of the Chequamegon-Nicolet National Forest in our study domain. And you can see that there are these patches of deciduous forest and patches of evergreen forest, and that there's wetlands and lakes. So it's a pretty heterogeneous ecosystem. And then looking at energy balance throughout the course of our study, this is a plot of the different components of the energy balance equation. This is the average diurnal cycle of all the sites over the entire study period. And so what you can see is in green, there's net radiation, and on the x-axis, it's hour, so it's solar noon is at 1700. And so you can see during the middle of the day, there's downward net radiation. And then in yellow and red are the sensible and latent heat fluxes. And during the day, those are positive. And there's also ground flux and storage, but they're quite small on average. And so when we add up all the components, we're left with a residual. So this is our non-closure term. And what we see is that residual also has a diurnal cycle. So it's weakly negative at night and strongly positive during the day. So when you average over an entire day, you get a net positive residual. We also see that energy balance varies on longer timescales, so seasonally. So this is a plot of the energy balance residual component averaged over an entire day. So it's a daily mean energy balance residual. And it's plotted for each point represents a different site. And so what you can see is on top of having this seasonal trend, so the seasonal trend here being in the middle of the summer, We have larger energy balance residuals, and then as we move into the fall, they get smaller. We also, though, see that there's significant variation across the domain. So energy balance is also varying spatially. And so, the next step here today is to kind of figure out how can we tie that to what's going on in the atmospheric environment. And so to do that, I'm going to use the Doppler wind lidar data set. And for the Doppler wind lidars, we had 3 halo photonics wind lidars. One of them was oriented in a vertical stare mode, and then the other 2, which were placed 90 meters away, were doing range height indicator scans. And so the 3 combined constitute a virtual tower and were capable of measuring 3-dimensional winds. And so that work was done by Luise Wanner, who's pictured here. She's at Karlsruhe Institute of Technology in Germany. And so those plots here, the plots here on the top 2 plots show the Doppler wind lidars data set for one day on August 21, just to get an example of what we collected. And so you can see the top plot is horizontal wind speed, and the middle subplot is the vertical wind speed. And so particularly with the vertical wind speed, you can really see that we have a very distinct difference between day and night. So at night, there's very little vertical wind speed, and during the day, we see these strong oscillations between updrafts and downdrafts. And so we believe those to be representative of mesoscale eddies. And so what we want to do with this data set is connect that to the energy balance equation and measurements that we took. So on the bottom subplot is the energy balance components for that day. And so the goal of this data set particularly is to identify the existence and strength of mesoscale eddies. And the variable that I'm going to use to do that is the angle of attack variable. So a combination of both the horizontal wind speed and the vertical wind speed. And these are column average angle of attack. And just like the vertical wind speed on the previous slide, you can see that there are these oscillations in angle of attack during the day. And then at night, it's much more calm. And that has to do with the stable boundary layer at night. So what we want to do here is zoom in just on the daytime periods. So this is just one day. It's the same plot, angle of attack over against time for just one day as an example. And what we did is we zoom in just to the daytime period, and we measure the average period in the oscillations of angle of attack. So on this day, it was 44 minutes. And we also measured the average amplitude of oscillations and angle of attack. And on this day, it's 4.2 degrees. And so these are what we're going to use to identify mesoscale eddies and the strength of them. And so the period and amplitudes measured across all our days. And so far, there's 51 days processed. There probably are a few more coming. And so on average, we see that the period of oscillation is about 37 minutes, but it ranges. And there's a mean amplitude in the angle of attack vectors of plus or minus 3 degrees on average, but our maximum is 6.3 degrees. And so to quantify mesoscale eddies in a useful way, we created this mesoscale eddy index. And for that, on each day, a mesoscale eddy index value is calculated. And that represents with equal weight both the mean period and the mean amplitude measured during the daytime period on that day. And each one of those was divided by the largest daily mean period and amplitude measured on any day during the study period. So for this data set, as I showed on the previous slide, the maximum period and amplitudes of any day were 55 minutes and 6.3 degrees. And so that's the equation I'm using for this data set. And so the way to interpret this is when index values approach 1, that represents strong mesoscale eddies. And as the values approach 0, that represents weak or non-existent eddies. And so what we see here is that when we plot the energy balance residuals against this mesoscale eddy index, we have a really strong relationship. There's an R squared here of 0.72. And so that at first sight says, oh, gives us confidence that mesoscale eddies are one of the major causes of energy balance non-closure. The other factor here, though, is the net radiation. So the color of the dots represents the net radiation during that period that it was measured, the daytime period. And you can see that there's also a strong relationship between net radiation and energy balance residual. And so this is partially to be expected because we would expect that on days where there's very little incoming solar radiation, there's not a lot of extra energy to have a really large energy balance residual. There's just not as much energy in the system. But the question then is, do mesoscale eddies still play a role, or is this just a factor of net radiation? But if we isolate periods with similar net radiations and then run a regression line through them, we find that there's still a relationship, like when binned in this way. And so that gives us confidence that there is some relationship. Now, these regression lines are not quite as steep as the original, so maybe there's, net radiation is partially responsible, but also it's clear that mesoscale eddies are, to some degree, playing a role here. And so to just get a quick and dirty kind of number on how much of an increase in energy balance residual we get on days with strong mesoscale eddies, we can just kind of do, we can see here how much increase we get across the range of mesoscale eddy indexes for each bin. And so what we found here is that for each grouping of net radiation, from the lowest mesoscale eddies to the highest in each bin, we see an increase of about 40 to 50 watts per meter squared. And so that's a sizable measurable component, but it doesn't account for all of the energy balance residual on those days. But the CHEESEHEAD project also collected an enormous airborne eddy covariance data set. We collected 480 flight legs or transects across the domain. That accounted for 72 flight hours over 12 days. And fluxes were measured at 100 and 400 meters above ground level. And this represents one of the largest airborne eddy covariance data sets ever collected. So what we can do with these is we can calculate fluxes using a wavelet decomposition. So the plot here shows a wavelet cross-scaleogram of latent heat flux. The y-axis represents the scale in kilometers, and the x-axis represents the distance across the flight leg. So this is just for one flight leg. The colors represent the strength of the fluxes. And so traditionally what you would do is you would integrate, at every given point along the flight leg, you would just integrate the cross-scaleogram, and you would get a latent heat flux. And so that's what the plot is on the bottom. So that's latent heat flux over space. But what's really cool about the wavelet cross-scaleogram is that we can also isolate length scales that we're interested in. So here we've isolated turbulent fluxes from mesoscale fluxes by isolating scales below 2 kilometers and scales above 2 kilometers. So then once we do that, we can plot the sensible and latent heat fluxes from turbulent and mesoscale contributions separately. So that's what's being showed here for August 23rd, which happened to be a day with large mesoscale eddy index. And what you can see is the blue bars are the turbulent fluxes, the orange bars are the mesoscale fluxes. And you can see that the mesoscale fluxes peak at around 40 to 50 watts per meter squared. And so when we compare this to a day that had a lower mesoscale eddy index, so this is the same plot for September 26, we see the mesoscale contribution is a lot smaller, so on the order of 10 to 20 watts per meter squared. So what we found is that we could use Doppler wind lidars and wavelet decompositions to isolate and identify mesoscale eddies. During this project, we found that energy balance varies across time and space, and we found that mesoscale eddies do increase energy balance non-closure. They don't account for all of the non-closure, but they possibly account for something on the order of 50 watts per meter squared. And if you're interested in learning more about CHEESEHEAD, there's an article coming out in BAMS that describes the project, but it's already online, so you can look it up there. All the data is on the Ankur data repository, and there's more information online at CHEESEHEAD19.org. Thank you for checking out the talk today. If you have any questions, please feel free to email me. My email's at the top. Thank you.